So, let us start today the application of Fourier equation to extract the concept of log mean area. So, this log mean area is defined as that area the application of which leads to conversion of radial systems into a plane wall system. So, the fundamental criteria which is followed in the case of log mean area is, by definition, log mean area gives the same heat flow rate for a radial system and a plane wall system for same temperature difference. So, in order to go into the mathematics behind this log mean area, that how this log mean area can be related with the area of the parent radial system, we have to derive the condition. The condition is the Q for this radial system that should be equal to Q for a plane wall system with this area of the plane wall system needs to be replaced with AM, that is the log mean area, where AM is the log mean area. Let us try to visualize this concept for a hollow cylindrical system. For, let us suppose, I am considering first the case of a cylindrical systems. The plan view of a hollow cylindrical system can be shown as follows. This is the inner and outer cylinders. The inner cylinder has a radius R1, the outer cylinder has a radius R2. This surface has a temperature T1, this surface has a temperature T2, and I am replacing this through a plane wall system having area, this area is replaced by the area AM that is the log mean area. So, this surface has a temperature T1 corresponding to this surface has a temperature T2 corresponding to the outer cylindrical system, and its thickness is R2 minus R1. Okay. So, Q for a hollow cylinder, Q for a hollow cylinder, that should be equal to 2 pi into K into L into T1 minus T2, if I am assuming that heat is being dissipated from the inner cylinder to the outer one. So, T1 minus T2 divided by log R2 upon R1. Let it be equation number 1, and Q for a plane wall, if area of this plane wall I am using the log mean area, then it is equal to K into AM, that is into T1 minus T2 divided by R2 minus R1. So, because of the fact that we are utilizing the log mean area here, so by definition these two quantities need to be equal with each other. So we can write that this quantity 2 pi K into L into T1 minus T2 divided by log E R2 upon R1, that should be equal to K into AM into T1 minus T2 divided by R2 minus R1. This K will get cancelled out, this T1 minus T2 will get cancelled out, or expression for AM comes as 2 pi L R2 minus R1 divided by ln R2 upon R1, or this can be further written as AM is equal to 2 pi R2L minus 2 pi R1L divided by log E 2 pi R2L divided by 2 pi R1L. This is the curved surface area of the outer cylinder. So, this is mentioned as A2 minus A1 divided by log E A2 upon A1. This is the relationship which is existing between A1, A2 and AM for a hollow cylindrical system. Now, extending this concept to a hollow spherical system, let us take whether there is a particular relationship between A1, AM and A2. So, considering another system, that is a hollow spherical system, the plan view will be same in this case also. So, in the case of hollow spherical systems, that is Q for the hollow sphere, that should be equal to Q for a plane wall system if area of the plane wall, that should be taken as AM, that is the log mean area. So, Q in the case of the hollow sphere, that may be given as 4 pi K T1 minus T2 R1 R2 divided by R2 minus R1, that I have given you in the previous classes. In the case of hollow sphere, this is the expression for the heat flow rate by utilizing the Fourier equation for the heat for the radial system without any heat generation. So, that is given as 4 pi k into T1 minus T2 R1 R2 divided by R2 minus R1, that should be equal to this quantity k into Am into T1 minus T2 divided by R2 minus R1. This will get cancelled out, k will get cancelled out. So, the expression for Am comes as Am is equal to, this will get cancelled out also, Am is equal to 4 pi R1 R2 or Am square that is equal to 16 pi square R1 square R2 square, 4 pi R1 square into 4 pi R2 square, that is equal to A1 into A2. It means Am is the geometric mean of A1 and A2. It means the series A1, Am, A2 form a GP, a geometric progression. This is the concept of log mean area. By utilizing the concept of log mean area, it is possible to convert a radial system into a plane wall system so as to impart some ease in the calculation made for the heat flow rate. So, this is the log mean area concept. It is my request to all of you to go through the numerical problem related with the log mean area in different geometrical conditions. This is of immense importance for the practicing engineer, that wherever and whenever you have to convert a radial system into the plane wall system, the area which should be utilized is the log mean area. So, it is an important design parameter for a design engineer. Now, come to the heat source system. The next thing of today's class is the discussion on the heat source system. Second is the heat source system. Let us take the case of a plane wall as shown below. How this plane wall is? This is the wall having faces. This face is at temperature T1, this face is at temperature T2. This surface has the coordinate x is equal to minus L. This surface has the coordinate x is equal to L, and this is the center line of this plate. This center line of the plate is chosen as a temperature axis in order to have a symmetry in the temperature distribution, as because this this plane wall is containing a heat source which is distributed uniformly throughout the volume of this plane wall, and so at the mid of the plane, let x is equal to 0, maximum temperature T naught can be achieved because of the fact that geometry of this section similar to each other. So the variation of the T naught to the respective wall temperature will follow the same pathway, and by doing so they will arrive at the same wall temperature, that is the T naught. So the quantity of heat flux or heat flow rate that is entering and the quantity of heat flow rate that is leaving the plane wall, that should be equal in the magnitude. So let us take the case of a plane wall. The shown plane wall has a heat source distributed throughout the entire volume. Now once you have arrived at the temperature, so you need to unnecessary to mention here T1 and T2 because both the wall has the same temperature, keeping the geometrical similarity in view throughout the entire volume. The two surfaces are at x is equal to minus L and x equal to plus L respectively. The temperature distribution has a symmetry about the center line, x is equal to 0, hence x barabar 0 is chosen as the temperature axis. This is all about the formulation of the problem. Now let us go through the Fourier differential equation for the present case. So Fourier equation for the present case, Fourier equation for the present case can be given as d2t upon dx2 plus q upon k x is equal to 0, right. So d2t by dx2 that is equal to minus q upon k, or dt upon dx that is equal to minus q upon k dx. Integrating this equation, you will find the temperature gradient dt by dx is equal to minus q upon k x plus C1. Proceeding further, you can write dt is equal to minus q upon k x dx plus C1 dx, integrating this equation again to arrive at the temperature profile in the system, that is equal to, after integration you will arrive at T equal to minus q upon 2k x square plus C1x plus C2. Let it be equation number 1. Now, as the solution of the differential equation, that is the Fourier equation for the one dimensional, here the assumption is here you have to assume an assumption the heat flow is unidirectional, because if you are not assuming the heat flow is unidirectional, then instead of this equation you have to utilize del by 2 T by del by x2 plus del by 2 T by del by y2 plus del by 2 T by del by z2 plus q by k is equal to 0. Because of the fact that I am considering the heat flow is taking place in only one direction, that is the x direction. So, the heat flow along the y and z axes is supposed to be insignificant, henceforth a 3-dimensional system may be converted into a 1-dimensional system, assuming that the heat flow is unidirectional in nature. So, integration constant as appears in the equation number 1, that needs to be evaluated from the existing boundary condition. So, the boundary conditions are, now come to the boundary condition. So, the boundary conditions are the boundary conditions are number A, T is equal to TW at x equal to L, and number B, T is equal to TW at x equal to minus L. Evaluation of constants C1 and C2, from the existing boundary conditions, will give the complete solution, of the temperature distribution, will give the temperature distribution or temperature profile fully. Now, equation number 1 plus condition A, utilize that condition. So, we can write T is equal to TW, that is equal to minus q upon 2k L square plus C1L plus C2, and equation 1 plus B, condition B, equation 1 plus condition B. So, it will again give you the TW, that is equal to minus q upon 2k L square minus C1L plus C2. So, q by 2k L square, because both will represent the temperature TW plus C1L plus C2, that is equal to minus q by 2k L square minus C1L plus C2. This will get cancelled out, imply that 2 C1L is equal to 0, imply that C1 is equal to 0 as never equal to 0. Thus, the value of the first integration constant that we have arrived is 0. So, first thing that we have derived is the C1 equal to 0. Now, C2. Now, the value of C2. Now, arrive the value of C2. Now, TW. TW, that should be equal to minus Q upon 2K L square, the C1 is 0 plus C2, or the value of C2 is equal to TW plus Q upon 2K L square. So, the value of the second integration constant as appears in the equation number 1 is this. So, you have obtained these two values, C1 is equal to 0 and C2 is equal to T naught TW plus Q upon 2K L square. So, the temperature distribution hence temperature distribution can be given as T is equal to minus Q by 2K x square plus C1x plus C2, the value C1 is equal to 0 and C2 is equal to TW plus Q upon 2K L square, or T equal to minus Q upon 2K x square plus this is equal to 0 and C2 is TW plus Q by 2K L square, or T minus TW has the expression equal to Q upon 2K L square minus x square. This is the T minus TW value. Now, at the center line, x is equal to 0, the mid T naught value. So, T is equal to T naught. So, putting in this fundamental equation, T is equal to T naught, that should be equal to 0, 0 and C2. So, this is TW plus Q by 2K into L square. So, the expression T naught, let it be question number 2, T naught minus TW, that should be equal to Q upon 2K L square. Now, divide equation number 2 by 3. Dividing equation number 2 by equation 3, okay, we will get T minus TW divided by T naught minus TW, that is equal to L square minus x square divided by L square. that is equal to 1 minus x by L square. This equation number 4 is called the temperature distribution equation in the dimensional. In order to convert this dimensional equation into a non-dimensional equation or dimensionless equation, you have to only transposing the sides only. So, 1 minus T minus TW divided by T naught minus TW, that should be equal to x by L square, or you can write T naught minus TW minus T plus TW divided by T naught minus TW, that should be equal to x by L square, or T naught minus T divided by T naught minus TW, that should be equal to x by L square, or T minus T naught divided by TW minus T naught, that should be equal to x by L square. Equation number 5 is the temperature distribution equation in non-dimensional form. So, this is the equation of the temperature distribution in both the cases, in both the forms, as dimensionless as well as dimensional form. Now, visiting this equation number 5, the equation contains even power of x. So, from the existing principle of the curve tracing, it means the curve has the symmetry about x is equal to 0, that is y axis, or temperature axis. That means this temperature distribution curve has a symmetry about this y axis. So, this thing can be established mathematically as well. Now, so far as the evaluation of this mid-wall temperature T naught is concerned, you can arrive at this mid-wall temperature in some alternate way as well. What should be the alternate way in order to arrive at the mid-wall temperature? So, the evaluation for the mid-wall temperature. Evaluation of mid-wall temperature, that is a T naught. In an alternate way, the mid-wall temperature can be evaluated by using the philosophy that whatsoever the amount of heat generated in the system, because I have said that this system has a heat source which is distributed uniformly throughout the entire bulk of volume. So, the philosophy is the heat generated that should be equal to heat lost at phases. By utilizing this philosophy that the heat generated, the entire amount of heat which has been generated in this plane wall system, that needs to be dissipated through the wall at x equal to minus L and x equal to plus L. Now, because of the fact that the heat generated in the system, because the heat source is being distributed throughout the entire volume, so if the heat flow rate is Q, then should be equal, then the heat generated in the system, that should be equal to Q into the volume, that is area into this length, because this point has the coordinate s equal to minus L, this point has the coordinate s equal to L, that means the value of this length is 2L. So, Q into A into 2L, heat lost at phases, heat lost at phases, because the two phases are there, this and this. So, that will be equal to 2 into minus K into A into the temperature gradient at x is equal to L, right. So, Q into A into 2L, that should be equated with 2 into minus K into A into dt upon dx at the value x equal to L. This A will get cancelled out, 2 will get cancelled out, imply that Q into L, that should be equal to minus K into dt upon dx at x. Let it be equation number let it be equation number 5. Now referring to the temperature profile, keep this equation view for some time. So, equation for the temperature profile, is, what was the temperature profile equation? T minus T naught divided by TW minus T naught, that should be equal to x by L square whole square, or T is equal to T naught plus TW minus T naught x by L whole square. So, the value of dt upon dx, that should be equal to, this is 0, this is constant, this quantity is also constant, TW minus T naught into 2 into x by L into 1 by L. So, the value of dt upon dx at x is equal to L, that should be equal to T naught, TW minus T naught into 2 into L by L into 1 by L, that should be equal to 2 by L TW minus T naught. So, equating these quantities in the equation number 5, you will get. So, we can write Q into L, that should be equal to minus K into 2 upon L TW minus T naught, or That can be further written as 2K upon L T naught minus Tw, or the value of T naught minus Tw arrives as QL square by 2K. So, the value of the mid wall temperature T naught is equal to Tw plus Q by 2K L square. This is the value of the mid wall temperature, and definitely that will be equal to C2. So, this is another methodology to arrive at the mid wall temperature. So, we have gone through this heat source system by taking the case of a plane wall. So, my advice to all of you that go through the radial systems as well, that means the cylinder with heat source and the sphere with heat source, for a thorough practice on the subject. Thank you. In the next class, we will see that what is insulation and what are the concept of insulation and what are the important design aspects there in order to prepare or design a proper insulator for all sort of engineering applications. Thank you.